Okay, so we'll keep going over confidence intervals today. Looking at, instead of the sample mean, looking at the sample proportion. Okay, so just kind of a little bit of a reminder. What we had was we would take our sample mean, we would then add our margin of error to it to get our upper bound. We used to subtract our margin of error to get the lower bound. We would go the number of standard deviations away that gave us alpha over 2 on either side of the confidence interval. Oh, it would help if I had this hooked up, huh, for you guys in class. All right. And then we multiplied that by, well, if we want to go 2 standard deviations away, we need to multiply 2 by the number of, whatever the standard deviation is. Now the equation we had for that was the square root of whatever the variance was we sampled from divided by our sample size. Okay? So that was our confidence interval for the sample mean. What we can do instead is we can also build a confidence interval for the population proportion. So if we remember a few things, that the population proportion, right, our sample proportion was centered around whatever that true population proportion was, right? Or the mean of those sample proportions is our population proportion. We also had this equation for the standard deviation of our sample proportions, which was the square root of, and here, p times 1 minus p, this really represented, right, the variance for the population proportion. So this represents the variance for our population proportion, just like we had kind of the variance for the sample mean, whoever the population was here, right? We're dealing with means. But now we're dealing with proportions. So let's go back there real quick. So we've got the variance of our population proportion, p times 1 minus p, divided by n, because we're looking at sample proportions of size n. We want to know the distribution of the sample proportions. And then we want the standard deviation, so we take the square root. Right? Well, we don't have the population proportion, right? The whole reason we're building this confidence interval is so we can figure out what range of values does this true population proportion fall between with a certain level of confidence, okay? So, well, instead of using the population proportion here, the best estimate we have is whatever we see from our sample, right? So we'll use this as the standard deviation of our sample proportions. Well, from there, as long as kind of this requirement is met, which I'll never give you examples where it's not, so don't worry about that. I'm just kind of putting that in there for, to be complete. Our confidence interval equation is going to look something like this, right? We're looking at sample proportions. So why does it look like that? Well, if we remember what we were doing with the sample mean, when we build a confidence interval, you take whatever the sample statistic is you're concerned with. Here, it's no longer the sample mean, it's the sample proportion. We're still wanting to add and subtract a certain amount to that to build our lower and upper bound. We can still use that standard normal distribution, right, to find out the number of standard deviations away we want to go to give us alpha over 2 kind of in those tails. Now here, instead of multiplying it by the standard deviation of our sample means, we multiply by the standard deviation of our sample proportions, which on that last slide I just said we can estimate with our sample proportion and plug that in there, okay? So the steps are going to be almost identical to what we were doing before. The only difference is we're dealing with sample proportions, right? So we center our confidence interval around that. And then our standard deviation for the sample proportions is a slightly different equation, right? But it's still the same general idea, okay? So one thing I think I mentioned last class, I always call like what you add and subtract to your sample statistic. I usually just always refer to that as the margin of error. It's really only technically correct to do this when we're looking at this proportion. And so kind of reminder, this thing that we're adding and subtracting to our sample statistic or our sample proportion here, I'm going to call this the margin of error. So whenever I say that, that's what I'm referring to. Okay? So let's say we had an example where we did this survey and 63 out of 81 people responded that they were in favor of covering pre-existing health conditions. Right? Let me make sure the chat's open here. Also, make sure the speakers are, okay. So 63 out of 81 are in favor of covering pre-existing conditions. Let's build a 99% confidence interval for what the true population proportion is for people that support this, right? So, you know, in this example, like if I have a policy that I'm trying to push through and I want to make sure that more than half the country, you know, more than 50% of people are in favor of it, I take a sample, I see 63 out of 81, well, it's higher than 50%, but if I had a pretty wide confidence interval, right? For example, let's say, you know, I don't know, what was it, 63, so 7/9. So what, about 0.77, I think. But let's say I build my confidence interval, and I don't know, it goes out past, you know, I don't, in this one you could have a really high value, but it doesn't make sense in this example. Let's say I went to 0.4. Well, then one of the true population proportions could be 0.5 or 50%, right? So this is the idea of why we might want to build this confidence interval. Other than that, so the first thing we have to do is figure out what is our sample proportion here. We're not like directly given a proportion, but if I have 63 out of 81, my sample proportion would just be 63 divided by 81, right? So if I'm thinking about what my sample proportion is here, 7/9, or that 63/81, just kind of simplified there. Our sample size was 81. That's pretty easy. We asked 81 people. Now for the 99% confidence level, right, our alpha would be 0.01 because alpha is the area outside the interval, or kind of the percent outside the interval in decimal form, right? So if we think about kind of these benchmark values, we'll see these pop up a lot. If I ever want, say, 0.9 in my confidence interval, or 90%, that'll always correspond to a z value of 1.65. If I want 99% in my confidence interval, or 0.99, that will always correspond to a z-score of 2.58, right? But why does it correspond to that z-score of 2.58? Well, if I go back here, remember, if alpha is 0.01, I look up alpha over 2, right? Because I've got two sides to my confidence interval. So alpha divided by 2 here, 0.01 divided by 2 is 0.005. I then go to my tables here. Oh, why aren't my tables showing up? Okay, let's try reopening this. Let's try reopening that file, I guess. Z tables. There we go. So I go to my table. The area I want in my tail is 0.005, alpha divided by 2. So I go through here. What's closest? Looks like these two. So negative 2.57 and negative 2.58. We said that that negative is already kind of built into our confidence interval equation. And so even though we found negative 2.58, well, it's already got the negative sign in here. And so we can kind of just take the absolute value, plug that in as the z value that we want, right? Because this was the number of standard deviations above our sample portion we wanted to go to get the upper bound, and the number of standard deviations below we wanted to get, or go to the left to get our lower bound, okay? So once we have 2.58 as our z-score, right, now we can find the intermediate step of find the standard deviation of our sample proportions, right? So this was the equation we had for the standard deviation of our sample proportions. My sample proportions simplified to 7/9, or 0.778. Plug that in, plug in my sample size of 81. I get 0.046. And now from here, it's just a matter of plugging those three values, my sample proportion, the z-score I looked up, and then the standard deviation of those sample proportions into my confidence interval equation, okay? Now I could have done this all on one line, right? Like here, I could have plugged in, 7/9 here, 7/9 here, 81, 2.58, and done this all at one time. Or I can break it down and calculate first the standard deviation of my sample portions, which I know is equal to this equation. Right? Whichever way is easier for you to go about solving these problems, that's fine. I think doing the intermediate way of calculating the standard deviation helps kind of solidify what we're doing with confidence intervals, because as we keep going, we'll start looking at different statistics and more complicated formulas for the standard deviation of the statistic we're looking at. But it's really always the same format. Take the sample statistic you're looking at, whether that's a sample mean or a sample proportion, find the number of standard deviations away from the mean you want to go, multiply that by the standard deviation of whatever statistic you're looking at. Okay? All right. So if we do that, we get this confidence interval of 0.66 to about 0.9. So we could say with 99% confidence, the proportion of people who are in favor of supporting pre-existing conditions is what? Somewhere between almost 2/3 up to 0.9, 90%. So this is definitely something that the majority, right, with 99% confidence, I can say the majority of people, way more than 50% here, are in support of this. Okay? Any questions on that before we keep moving? We're good? Let's go through another example here. So if we went back to the last election, right, there was some survey data that came out prior to the election. I believe this is actually, I think when I got this, it was from Fox, because I was trying to find the one that would be kind of biased. So out of these 912 people, 46% said they were planning on voting for Clinton in the upcoming election. So we could actually build a 90% confidence interval for what the true proportion of people who are going to vote for Clinton would be, right? Because we've got our sample proportion, 0.46. We have our sample size, 912. What would our alpha be here at the 90% confidence interval level? 90% alpha would just be 10%, or did you say 5%? Yeah, so this is where we gotta be careful, right? When we think about what is alpha, alpha here would be 0.1, right? But the area that we actually want to look up in the table, because we need to look up the z-score that gives us alpha over 2, so 0.1 over 2 would be 0.05, right? So be careful when you're thinking about alpha. Alpha is the total area outside your interval. You know that half is on each side, and so you're going to be looking up alpha over 2. Yep. So we go down here, and just kind of a reminder, right? These are our benchmark values. We want 90% in our interval, or 0.9. That's always going to correspond to a z-score of 1.65. Why? Because we look up alpha over 2, and here alpha over 2 we said was 0.05, so we go try to find that, the area that matches that. So 0.05 is in between these two values. So negative 1.64 and negative 1.65, we'll take the higher of the absolute value of those two, so 1.65. Sure enough, that's exactly what I was telling you kind of in these benchmark values. And it'll always be the same, right? If I keep looking up the same alpha over 2, the same value, I'm always going to find the same corresponding z-score, right? So we'll see these z-scores pop up a lot, okay? So back to the example, we identified the piece of information we need. We looked up that z-score. We could calculate the intermediate step if that's the way we wanted to do it. We get about 0.0165 here. Now it's just a matter of plugging those values into our confidence interval equation, and we get this range of 0.41 to about 0.49. Right? So, erase this here real quick. So I'm kind of give you this thought experiment. Right? So 0.41 to about 0.49, right? So 0.41, 0.49, and a 0.46 was right in the middle. Right, is it 0.46? Hold on. Doesn't make any sense. Oops, that's not what I wanted to do. So 0.46, 0.4. Is it just my rounding here? Here. Let me make sure I didn't make a math error here. 0.43, okay, that makes more sense. Must have a typo there. There we go, that makes a lot more sense. Okay, so 0.43-ish. Yeah, that's what it should be. So why did I know that was wrong? This was 0.41. Why did I know that there was some typo where I made a mistake there? Exactly, right? When I look at these, my sample proportion should be smack dab in the middle, right? So I need to do a better job of looking at those values in my size, because like if you look at those right away, if I'm looking at, well, this is further away, that can't be right, right? Okay, so let's keep that in mind. That'll be floating around in the background. We're going to look at that same exact poll, but they had the percent of people who are going to vote for Trump was 40%. So we could do the exact same thing. The only thing that's going to change, if we do a 90% confidence interval for the proportion of people who are going to vote for Trump here, is our sample proportion is now 0.4. So when we calculate that standard deviation of our sample proportions, we plug 0.4 in here, okay? So then I go ahead, I plug kind of this in here to my confidence interval equation, and I get what, about 0.37 to point, if I round up on this one and down on this one, 0.43. It's not exactly right. I should probably put the right exact numbers. But here, 0.43. What was it? 0.4, 0.37 was my lower bound. Right? Now, I probably should keep the more than just 2 decimals on this because it's going to look like, it would be a good kind of discussion here. From this, I could, let's say that the lower and upper bound were both exactly 0.43. I actually couldn't say that Trump was going to receive a lower proportion of votes than Clinton. Because what could be true? Well, yeah, these are all possible true values for the population proportion of people that will vote for Trump. So it could be that the true population proportion is somewhere like here. And it could be true that for Clinton, it was somewhere right here, right? However, it could also be true that for Clinton, it could be exactly 0.43, and for Trump, it could be exactly 0.43. In which case, right, they're the same value. I can't actually say that one's going to be higher than the other. Now, I think if we actually go out to the more than just 2 decimals, or well, here, this is going to be something like, what, 0.428, and this is what, 0.432, I don't know, it ends up being something else to the 3rd decimal. And now you can see, well, now actually, if Trump, at the 90% level, if we took the highest value in that confidence interval, and we took the lowest value for Clinton, her population proportion would still be greater than his, right? And so this would be, allow us to say, well, yeah, I can, with 90% confidence, I can say that Clinton's going to receive more of the popular vote than Clinton will. Sorry, Clinton will receive more than Trump will, right? Now, what happens if instead of the 90% confidence interval, I wanted to be able to say this with 99% confidence? Well, if I increase the level of confidence I want to say something with, what happens to alpha? So if I increase the level of confidence going from 90 to 95, alpha goes from 0.1 to 0.01. So before, the z-score of 1.65 that corresponded to an area of alpha over 2, which is 0.05. Well, if alpha is 0.01, the area I now want in the tail is 0.005. So I'm going to have a larger, in absolute value, a larger value. So this will be, I think, negative 2.58, right? So that's going to go back into my confidence interval equation as a higher z value. So my margin of error is going to be larger, and my confidence interval is going to get wider. So if I go to the 99% level, everything else stays the same. What's going to happen is this is going to move out farther. This is going to move out farther. This one, I didn't leave myself much room, but it'll go out farther. This will go out farther, right? And now at the 99% level, well, the true population proportion for Clinton could be here. For Trump, it could be here. Or it could be Trump's over here, Clinton's over here, right? So I can't really say. I don't have any idea. If these confidence intervals overlap, I can't really say whether or not one of these population proportions is going to be higher than the other. But when they didn't overlap, then I could say with that level of confidence that the one that was higher will have a higher population proportion, okay? Any questions on that? I know I kind of went through things quick. I'm trying to draw in a lot of different ideas to this example, okay? Any questions over anything I said there? Okay, all right. So I thought it'd be kind of interesting to do the same sort of setup for this upcoming election and see if we can predict it and get it right, right? So one thing that's actually interesting, if we think about that 90% prediction that Clinton would have a higher population proportion, that is actually what ended up happening. You can go back and look at the data. Now, if we want to do the Electoral College, it'd be a whole different exercise that'd be a little more complicated, and I'll probably talk about that in a second. But let's say we just want to predict the popular vote, right? Let's say I want to do a 90% confidence interval, right? And this is, I didn't change it here. I tried to copy and paste a little bit. Right. So let's say there's a recent poll, and I actually went out and got this. NPR kind of put out some data they found from a survey. So they had almost 1,200 people, and 43% said they plan on voting for Biden. Derive a 90% confidence interval for the true proportion of the U.S. that will vote kind of for Biden here. Right? So 0.43 is my sample proportion, right? 90% confidence interval, I'm still going to be using that z-score of 1.65. I plug everything in, and I can end up with my lower and upper bound here, right? Same sort of exercise as what we just did, right? This is not making any sense. Oh, I know what this was. I flipped these around. Give me 1 second here. This one was 43, 54. So this one should be, I remember this now. And I'll pull this up here in just a second, the actual website. So this was Trump, and then I went Biden next on this one. And this next one should be Trump and Trump. So I'll get these, I'll re-upload these files as soon as we're done with class here. Because I do think this is an interesting example. So I take that back. The first poll that I had was there's 1,200 people, and 54% said they were going to vote for Biden, right? So I want to do the 90% confidence interval. I use that sample portion of 0.54. Everything kind of follows where I've got this lower and upper bound, right? It's the exact same process that we did before, right? Now notice that when I get kind of this higher sample size, it's going to drive my standard deviation down quite a bit. So what that allows me to do is really narrow in this range of values, right? If I only taken, you know, a sample size of 199 people here, well, this is going to be a very wide range, right? It's already a range of about 0.05, which doesn't sound like much, but for a proportion, it's a pretty big range, right? So we've got this lower and upper bound. We could then look at, there we go, that same survey found that 43% of people said they were going to vote for Trump. So we could build the lower and upper bound for that, right? And now we can essentially just plot these confidence intervals and see, do they overlap or do they not, right? So 0.4 to 0.45 and 0.51 to 0.56, right? So it's the same sort of idea as what we did in the previous example, but now we've got what was it? I'm already forgetting what these were. But 0.51 to 0.56, so 0.51, 0.56, and then 0.4 to 0.45. Okay. So just for the video, I'm going to go here. So you can clearly see that the lower bound for the confidence interval on the true population proportion of people that will vote for Biden is much higher than the upper bound for the population portion of people who are going to vote for Trump. So given this data, what we would say is with 90% confidence, we can say that Biden here is going to get a higher proportion of votes than Trump would, right? Now, we got to factor in there was some undecideds in there, right? So I think we're missing like 3 or 4% in there. So that's something that, you know, to actually make a real political prediction, this would be a little more complicated, but this is like a first step, right? So kind of interesting. I was a little concerned with that poll. So I looked up a different one. This one was done by, oh my gosh, what's the name? They predicted the Rasmussen. So they predicted the last election correct when a lot of people didn't. So when I look at their data, they had a few more people in their survey. Automatically good, right? Because we can really narrow down this range of possible values. They had 51% of people planning to vote for Biden, or sample portion of 0.51, right? So we plug that in. We're keeping the same 90% confidence, so it's going to be that same z-score, right, every single time. And we got 488 to 0.53. We then look at Trump, and this should be, sorry, this was the Still the Rasmussen. I really should have went over this more. I was trying to put this together late last night because I thought this was a really cool example. This was from the Rasmussen poll, so this one had slightly higher people. Forgot to change these in the slides. I did all the work in Excel, so that's why. All right, there we go. So if we look at the Trump kind of vote, it was 0.43 as well from the Rasmussen poll, right? It's kind of interesting, right? Two different surveys found actually the same sample proportion. Now, it was obviously not exactly 0.43, but really close. So we look up that Z-score, it's still gonna be 90%, so it's the same Z-score. We plug in our sample proportion here, and now we get a lower and upper bound of what, 0.44 and 0.49. So now notice Trump's upper bound is actually higher than Biden's lower bound. So there is some overlap if we looked at this poll, right? Which, you know, I don't know exactly, I didn't read through how they, you know, got their sample. I don't know how Rasmussen did it differently than the NPR poll, but you know, it does kind of give us some pause that, you know, even though we see these sample means are pretty far from each other, 0.51 and 0.43, even with a pretty high sample size, we still can't actually say that one is going to be higher than the other. And in fact, if we want to do this at the 99% level, remember, that's going to widen our intervals. We for sure couldn't say it here, right? So I don't know, I think it's an interesting exercise. Also maybe gives you less faith when you look at political polls and their actual predictions. We already talked about the potential bias that exists in these, but it is, you know, I mean, 1,500 and 1,200 is a pretty high sample size, and we still aren't really able to kind of make this statement with 90, 95, or 99% confidence, okay? Any questions over any of that? Like I said, I kind of put this example together last minute because I thought it'd be interesting, and it was kind of relevant to what we're talking about right now. Any questions on that? So I have a thought experiment. I want to see if anyone can follow along. So what would I actually need to do to get a good idea about the Electoral College outcome? If I was trying to use what we just talked about to predict the popular vote for the entire country, what would I need to do in order to kind of predict the electoral vote? Well, what am I wanting to find there? I need that in, say, one state, let's say Indiana. I want to know, will more people, or will there be a higher population proportion of people that vote for Biden than Trump, or vice versa? So I would do this same exact thing. I would sample only people from Indiana. And I think actually, in fact, these polls even mentioned, they tried to, after they did their sample, they actually took people out that based off of their response weren't likely voters. So we might want to try to target like likely voters, do this same sort of thing, but only with Indiana residents, right? And then if we can find that the population proportion is going to be higher in Indiana than, you know, for Trump than Biden or vice versa, then we could predict who's going to win Indiana. Well, you can already see we can't really make a prediction even with 1,500 people. So if we have to go out and get 1,500 people from Indiana, and let's just say best case scenario, the confidence intervals don't overlap, well, that's one of the 50 states. So we don't need 1,500 people, we need 1,500 times 50 people, right? We'd have to get that sample from every state. So, you know, it makes it really hard to make these predictions, right? When you look at these polling stuff, you got to take it with a grain of salt, because I mean, that's a lot of people. It's a really high number of people. And even when they were doing it nationally, they could only get, what, 1,500 and 1,200 here, right? So it would kind of, you know, grow the sample sizes you need pretty exponentially if you wanted to try to predict that Electoral College outcome. Okay. Any questions on that before we keep moving? I thought that's somewhat interesting, pretty relevant. So we're going to kind of go back to thinking about sample means. So one of the things that we saw come up with the sample proportion was, well, look, we're trying to build a confidence interval for the sample proportion. If the standard deviation of my sample proportions is equal to this, well, the whole reason I'm building the confidence interval is because I don't know the population proportion. So, right, we had to use the sample proportion as our best estimate. Well, think about with the sample mean, right? If we're trying to build a confidence interval for where the true population mean is, part of the equation we had in the confidence interval was that we had the population variance. How the hell do I have the population variance if I don't have the population mean, right? Well, I kind of gave you this kind of cheap, explanation of, well, sometimes, you know the variance on the machinery or the production process when you can pull only a sample off the production line. And that's true, but in more cases than not, we aren't able to observe what that population variance is, right? If I think about like the population variance on height, I don't have some machine that I know that the population variance. I can't see the population data. The best guess that we're going to have for that is our sample variance, right? So if we don't know the population variance, right, we actually just use the sample variance. From there, everything's the same, right? So if I look at, if I want to look at my confidence interval equation, when I don't have the population variance, well, I'm still going to be building it around my sample mean, right? I'm going to want to go a certain number of standard deviations away. So before we were thinking about this as a z-score. And then now I'll have the sample standard deviation of my sample means, right? Because now instead of taking the square root of the population variance, I'm using my sample variance. Okay? So, I mean, once you plug the numbers in, it's going to look identical to what we were doing before. Now, one other issue is we actually aren't using z-values anymore. So because we're using the sample variance, we're going to have to start using something called the student t distribution. Okay? So we're going to have to start using this student t distribution, and we'll return to this here in a second. I want to set up some more stuff. If you go on Canvas, go to Files, I'll add it right here, so we'll just be on the main page, so that we'll have kind of those t tables, right? So actually, I'll just do that right now, as long as we're here. I didn't know if we'd get this far this week. So we're just going to kind of introduce the idea today. We probably won't get to any examples, but if I have to use that sample variance, I'm not going to be able to use that standard normal distribution. Think about it. If I converted things into z-scores, part of my z-score equation was I divided by the standard deviation. Right? Well, now I'm not dividing by the population standard deviation. I'm dividing by the sample standard deviation. And because part of that equation is dividing by n-1, right? When we calculated the sample variance, we said the difference between the sample and population variance is I divide by n-1 instead of n. So when I have smaller sample sizes, that's going to mess around with my sample variance a lot more. So if I have a sample size of 3, dividing by 2, n-1 would be 2, instead of 3, we'll change that number a lot more than if I divided by n is 1,000. So instead of dividing by 1,000, I divide by 999, right? That doesn't cause near as much of a change. So every time we look at a sample mean example where we only have the sample variance, the distribution, once we try to convert these into z-scores, we'll actually be converting them into t-scores, because we know that it won't follow a standard normal distribution. It'll follow something very similar, but it's going to be more spread out, right? So it's going to have a mean of 0, right? These student t distributions, they'll have means of 0, but the variance is going to be higher than 1, okay? Because the standard normal, remember we said had mean 0, variance 1. The student t distribution, right, is going to have a mean of 0, but it's going to be much more spread out. And when we say the student t distribution, it's really being a little bit lazy with our language, because it's really a bunch of student t distributions. For every single sample size, we'll have this thing we call degrees of freedom. Every different sample size has its own student t distribution, right? So technically there's an infinite number of student t distributions, 1 all the way up to infinity, okay? Or sorry, not 1, but we'd start out at degrees of freedom of 1, so we would need at least a sample size of 2. So this degrees of freedom is just going to be n-1, right? Kind of corresponding to that, what we're dividing by in that sample variance equation. So for every single different degrees of freedom, which really corresponds to every single different sample size, there's going to be a different student t distribution, okay? So the nice thing about the student t distribution is it still has a mean of 0 and it's still symmetric, right? That helps us out a lot, okay? So a lot of the same principles we were talking about with the standard normal distribution, all those same principles apply. Now the problem is that the standard deviation, or that variance, is no longer 1, it's going to be a little bit higher. And as we have higher and higher degrees of freedom, it becomes less and less spread out. All right? So really small sample sizes will have a variance much higher than 1. But if I get to a sample size of like 1,000, my variance will be very, very close to 1 for these student t-distributions, okay? In fact, if I can get up over 100, the student t looks no different than the standard normal distribution, right? It's a really close approximation if I just use the standard normal for a student t-distribution over degrees of freedom of 100, okay? Now, most of the times, we have samples less than 100, so this is going to be relevant that we know how to use the student t-distributions when we have sample sizes that are lower than 100. Okay? So the idea of these student t-distributions is, let's say I start out with a standard normal distribution. Right? If instead I was looking at a student t-distribution where my degrees of freedom is 20, what I know is that these student t-distributions have a higher variance than the standard normal. So if I have a higher variance, that's going to flatten out my distribution. So notice that student t-distribution for degrees of freedom of 20 is going to be flatter, right, or kind of squashed down, such that values around the mean are less likely to be seen, and values further from the mean are more likely to be seen in the standard normal distribution. Okay? Now here's where we kind of have a problem. Let's say, and here's the degrees of freedom of 5, right? As I get a smaller sample size, variance just gets higher and it gets more flat. Well, here's the problem. What we eventually want is this, right? This confidence interval. But before, we were looking up z values that would give us alpha over 2 on either side, okay? Well, if I were to choose those same values, say 1.96, which for the standard normal distribution gave us kind of the area underneath the curve and to the right of the standard normal distribution was 0.025. But notice, what would the area under the student t-distribution curve be to the right of 1.96? Well, if this area underneath the black curve is 0.025, it's a larger area, right? And so I actually need to go out more than 1.96 standard deviations from that mean when I'm using that student t-distribution. Okay? In fact, if we look up those values, for the standard normal distribution it would be 0.025. For the degrees of freedom of 20, it's 0.062, and degrees of freedom of 5 is even larger at 0.068. Right? So we won't be finding the same values anymore when we're using the student t-distribution that we were for the standard normal. And I'll give you another way of looking at this because I like that picture, but I think it could be, I think if I draw this out, maybe it'll help even more. So let's say we've got, I don't know, standard normal distribution here. I'm going to really exaggerate. Let's say I have a student t-distribution. So t with degrees of freedom of, I don't know, we'll just say 30 or something, right? So this flatter curve is my student t-distribution. If I were to choose 1.96, this area is 0.025. Well, it's very clear the area under the student t curve to the right of that is a much larger than 0.025, right? And so how do I get this area to be 0.025? I'm going to need to choose a higher cutoff value until I can get that area down to 0.025. Okay? So that's the idea of what we're doing. And how we're going to do this is we're going to use the student t table. Okay? So this is kind of a truncated version of it. I'll show you the real version here in just a second. But what we're going to do now is it works kind of a little bit in reverse of the standard normal table. So now if we know the area that we want in the tail, we're going to use these column headings. So this represents the area in the upper right tail. So unlike the standard normal distribution table, it's always looking at the area to the left. The standard normal is going to kind of look at the area to the right. And really the reason why is because most often, right, when we're doing things like confidence intervals, which is what we're primarily using this for, we were dropping the sign anyways, right? When we looked up alpha over 2, we always dropped the sign. So by looking at that upper right tail, they're just always going to be giving you the positive values, okay? So we have different degrees of freedom here. So once you determine what your sample size is, let's say I have a sample size of 51. My degrees of freedom is just n minus 1. So 51 minus 1 is 50. So I look up my degrees of freedom, 50 row. Then let's say I wanted an area of, I don't know, 0.025 in the tail. the value that would give me that is a t-value of 2.01. Right? So we said that the t-value would have to be higher than 1.96. Sure enough, it was 2.01, right? And if we look at any degrees of freedom, right, all these are higher values than 1.96, okay? So that's how we use the student t-table to kind of find the t-value that would give us whatever the desired area in our tail is. And this is one tail, right? Now, another thing to mention is, remember I said as we go get sample sizes over 100, or as the sample size gets larger, we get a student t-distribution that's a closer and closer approximation, or sorry, that gets closer and closer to looking like the standard normal distribution. So if we could have a degrees of freedom of infinity, which in practice, right, is impossible. We can't get a sample size that has an infinite number. But if we were, right, these values that we would get would actually be exactly the same values from that standard normal distribution. Because at degrees of freedom of infinity, the student t-distribution actually becomes the standard normal distribution, okay? But you can kind of see, even at 100, right, we're only off to like the second decimal. We're not even actually off that much. If we kept out to the third or fourth, they would see they're really, really close. Okay? So I'll show you the actual table. Maybe that I posted for you guys. And here's one thing I want to mention about this table before I get going. I don't like how this has this up here. If I can find a better table, I'll post it. You can cross this off. Like if you are printing this out and looking at it, cross this off. So this looks like alpha because it's just telling you that this is what alpha is. Well, in our problems for confidence intervals, alpha is the total area in the tail. So here, when it's referring to this as alpha, that's not the same as the alpha from our problem, right? This is just the area in the tail. So I would cross this off, or right here, alpha divided by 2, because that's really what these would kind of represent, right? These are just the area in one of those tails, okay? So we'd really, let's say I had an alpha of 0.1, right? I wouldn't look up in this column. I would actually look up alpha over 2, right? 0.1 divided by 2, so I'd actually be looking up 0.05, right? So I would just cross this off not to cause any confusion. This table is only telling you the area that's in one of these tails, right? And the area that you want in one of those tails for confidence interval problems is alpha divided by 2, okay? Notice this one has a few more values in it. Actually goes up here and then starts to make some large jumps. Notice at the higher sample sizes, I mean, these are off to the third decimal, but it just becomes a closer and closer approximation to these values that we would get from the standard normal distribution. And one nice thing about this table is I can actually be a little bit more accurate now when I'm dealing with my sample proportion and sample mean problems when I had a population variance, because now if I go down here, it actually is giving me the z value for this area in the tail out to the third decimal. So instead of like being in between two values now, we can actually get a z-score that's out to the third decimal instead of just to the second. We can still use the standard normal tail, that's fine, but I mean, it's all right here for you. And these are, the area in the tail here, a lot of these are our benchmark values we want to use for the 90, 95, 99% confidence levels, okay? All right, so all this being said, right, we can kind of use this confidence interval equation. Now, instead of using the z-value, we use the t-value at whatever our degrees of freedom is that gives us alpha over 2 on each side of our confidence interval. We then multiply that by the standard deviation of our sample means, but now that standard deviation of our sample means is kind of like thinking about it as like the sample standard deviation of our sample means, right? Because we're no longer using the population variance, we're only using the sample variance, okay? So the steps are really going to be the exact same, right? So we're going to identify the piece of information that we're given. Now, instead of looking up a t-value, we look up a z-value. We still calculate the standard deviation of that sample mean as the intermediate step, and then just plugging things into our lower and upper bound equation. The steps haven't changed at all, with the exception of we now need to look up a student t-distribution. Okay? And it's because all we have is a sample variance, not the population variance. All right? Any questions on this? All right, so I think what I'm going to do here. I wanted to introduce that idea. I'll start next class. We'll do some examples with this, and then we'll go to Excel and we'll see how do you do sample proportions and sample means where we only have a sample variance, and we'll do quite a bit of Excel work on Monday. All right, so we'll do these kind of a quick review and do these few problems, and then we'll primarily be kind of focusing on Excel. All right. One other thing I wanted to mention, I was looking kind of at the syllabus and just kind of where we're at. I'm going to move the exam date up a lot so that we have more time for the later material in this class. So when we go online, I mean, because I know when we go online, it's going to be difficult. And that date was kind of set to be like before we left for Thanksgiving. I'm going to pull that back a few weeks. So I'll get that posted on Canvas about what that date's going to be. I'm tentatively thinking about November 11th, which is a Wednesday. Would still give us plenty of time to do some review prior to it. But I'm going to kind of cut us off in terms of material at an earlier point, and then kind of package the end of the class a little bit differently. Okay. I think this will end up helping. I'm pretty positive that this is going to end up helping you guys out, censoring, kind of cutting off at an earlier point as opposed to a later point. Any other questions from me before we get out of here? Remember what's due at the end of the day today, that Connect assignment. All right, push that due date up until today at the end of the day. Other than that, after Monday, you should have everything you need to kind of work completely through that Excel assignment. We've already done some of the confidence interval stuff last class for, I think, problem 2. And then Monday we'll finish up so you can do problem 3. Okay? Questions for me? Otherwise, I'll see you guys Monday. Have a great weekend.